All right, so we're continuing on with this example where we're talking about big trees, small trees, short trees, and tall trees. It says that the Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. The question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the study area, or steps of the forest compare. To find out, researchers took random samples of 30 trees from each half. So notice I just read 30 trees, and so remember I told you that I pay attention to sample size, because when I read, because that's important, because I know that if it's not greater than 30, I'm going to have a problem. But I'm so excited that it's 30 because the central limit theorem is going to apply for me. And so those are things that I train my brain to look for when I'm reading these problems, and you should be doing the same. It says, from each half, and measured the diameter at the breast, which they called the DPH, in centimeters. Comparative box plots of the data and summary statistics from Minitab are shown below. Construct and interpret a 90% confidence interval for the difference in the DBH for longleaf pines in the northern and southern halves of the Wade Tract Preserve. So they show you these box plots. We really doesn't matter about the spread as far as determining a normality here, because we have a sample size of 30, so it's at least the 30 we need for the central limit theorem to apply. They tell us that they took a random sample from both of, the northern and southern. So it says random samples, so we know the random condition works. And then I'm going to go ahead and assume that there's more than 300 trees in the North and the South Preserve, which is going to be our independence condition. But you'll see that. So they're going to state that our parameters of interest, mu, is the mean, the true mean of DPH of all trees in the southern half. So southern is going to be group 1. All right, so I would note this, that this is group 1, and then this is going to be group 2. Okay, so this is going to be the mean of group 1. Now, this is the statistics, so this is going to be my x bar. Remember, we're going to make conclusions about the mu, but this is my x bar. This is the standard deviation. All right, so, and this is group 1 and group 2. So we have to remember that and keep it organized while we're working here. And so then the mean mu2 is the DBH of all trees in the northern half, and we want to estimate the difference in the two at a 90% confidence. So the plan, we tell them we're going to do a 2-sample t interval for mu1 minus 2. So if the conditions are satisfied, so remember this is going to be southern minus the northern part, because group 1 is the southern and group 2 is the northern. So random, the data comes from random samples. I told you it's normal because they're both greater than 30, so it doesn't, it doesn't matter if they're normal. Like if the box plots show normality, our sample size are large enough, so we're good with our T procedure. And then independent, like I said, there's more than 300 trees in each part of the forest. So since our conditions are satisfied, we can construct a 2-sample t interval. Remember, it's a 90% confidence. So the thing is here is that they have the same n, so our degrees of freedom is 29, all right, for both of them. If they weren't, we would have to take the smaller, the 2 degrees freedom, or use the df from the calculator. All right, and so at this point, before I even start my do step in my calculator, I would run my do step. So I would go to menu, statistics, confidence interval, and I have a 2-sample t interval. And I have statistics, so it's going to ask me my x bar from group 1. So remember, my x bar from group 1 here is going to be this 34.53, because remember, group 1 is the south. And so this is going to be the 34 point, let's have it bring up. 34 point, sorry, 34.53, 23.7. Go ahead and write that down. 34.53. My X bar happens to be you guys should be filling this out looking at your PowerPoint because I just had to grab them. It's going to be this 17.50. So no, it's 14.26. 14.26. And my sample for the group 1 is 30. My X bar for group 2 is 23.70, 23.7. My standard deviation, that's the 17.5. And again, my sample size is 30. And then it's going to ask me for my confidence level, and my confidence level is going to be 90%. And so when I go ahead and run this in the calculator, notice it tells me what my degrees freedom is. It's 55.72. It gives me my margin of error, my X bar difference, my lower, my upper, my X bar 1, my X bar 2, and all of that. But this is really what I'm worried about is this degrees of freedom. So it's the 55.72. They don't then give you the critical value. So in your sheet's not going to, the only thing is that if you run in the calculator, you're, it's not going to tell you what that is. So if my X bar of group 1 minus the X bar of group 2 plus or minus T critical, all right, and you're going to write degrees freedom 55.5 something if you're running this in the calculator, times, and it's going to be the standard deviation of the statistic, which is going to be standard deviation group 1 over N1, right, squared plus standard deviation of group 2 squared over N2. Okay, and you can plug in all your values, so I'm going to just go ahead and let them know that I'm doing this of the 34.53 minus this 23.7 plus or minus the T critical times the standard deviation, which is the 14.26 squared over 30 plus 17.50 squared over 30. And then this is going to become your margin of error, which you get from your calculator, and it's going to be 6.89383. So 6.89383 plus or minus, and then again for my calculator I know it's 10.83, so 10.83. If you show this and tell me that your degrees of freedom is the 55.5, which is what the calculator gives you, I won't make you have this critical value. If you don't run it in the calculator, you need to find this critical value, or at least still find it. Oh, let's see. I think you should still find the critical value. So at a 90% confidence level, use degrees freedom of 29 to get a T critical. I'm still going to ask you for the T critical even if you run it in the calculator, which uses the 55.5 degrees freedom. So yes, you do have to get me a T critical using 29 degrees freedom or whatever one is the more conservative one off your chart. So if you do that, you have to go to your chart and you have to look up on your T chart what your confidence interval or your critical value will be. Just because I want to make sure that you know and that you can get it and all that stuff. So my 90% confidence interval for T critical at 29 degrees freedom is 1.697. If we did 50, it's going to be 1. So this is 1.697 for 90 degrees freedom, or 29 degrees freedom. Sorry, 6.99, 97 is 30, so 6.99 is what needs to be put in there. So you can write 10.83 plus or minus. Your critical value needs to be 1.699, or if you used the 55 degrees freedom from the calculator and so you're getting a T critical, you would have to use degrees freedom of the 50 line, because you don't have a 55.5, and if you did that, then your critical value would be 1.676. So 1.676. I would accept this as a T-critical or this as a T-critical. And notice why. This one comes from the chart where I use degrees freedom of 50, and I use degrees freedom of 50 because I can't use 55, which means I drop down to 50. Or I use the conservative method, which means I have to use 29 and get this. These are the only two answers for the T-critical I'll allow you to have in here for your work. And then you can carry on with your margin of error and add or subtract it here. All right? So notice I'm only letting you use either this or this, okay? The only other thing I would let you use is if you actually worked it out in 55 degrees freedom, so a DF of 55 exactly, and you did 90, which would be 0.05, and you used inverse T to find this. And some of you are like, what? Yeah, just, if you don't know what I'm talking about, that just means you're not supposed to use that method. All right, and then do your value. So look, they get 1.699, all right, because they use 29 degrees freedom. So it comes out to be this, 3.83 to 17.83. So they conclude it. We are 90% confident that the interval from 3.83 to 17.83 centimeters captures the difference in the actual mean breadth. Okay? So if it differs from 3.83 to 17.83, would we be able to conclude there's a difference in the diameter of the trees from the south to the north? Yes, we would be able to conclude that.